We're being asked to convert -2, -5 from Cartesian or rectangular coordinates into polar coordinates. First and foremost, actually, r is easy to find with the Pythagorean equation right here. So we get that r squared equals -2 squared plus 5 squared. And this is really straightforward, is that r squared equals 4 plus 25 is 29, which means that our r value equals the square root of 29. So we found r, now we just need to find theta. What we're going to use is this fact that the tangent of theta equals -5 over -2, but I'll just write that as 5 over 2 because the negatives cancel. Now importantly, I'm going to apply the tangent inverse to both sides of this. I'm going to do this somewhat quickly, really just as a suggestion for how you're attacking that you do the same. So in this case right here, I'm going to take the tangent inverse of both sides, but I know that the angle that they're going to output is somewhere in the first or fourth quadrants. So what I'm going to do, when I take the tangent inverse, I apply it to both sides, I get the tan inverse of 5/2. But what I'm going to do, importantly, is I'm going to add pi to that. So I'm adding pi to get an answer for theta that will have an output or have a tangent value of 5/2, but be in the third quadrant. I do this whenever I have a rectangular coordinates that end up in the second or the third quadrant, anywhere over here, because I can't output those theta values from tangent inverse. So that's just a little trick to remember right there. And again, that's why I say just plus pi, because that will always be the trick when you're going from rectangular into polar to get it into the right spot. But I digress. Let's do this. So when I apply this, I got that the tangent inverse of this was about 1.19. Add pi to that to get a theta value of 4.33. So there's the work for converting this from a rectangular coordinate system into polar. And again, I found r by using this Pythagorean relationship right here between x squared, y squared, and r squared. I find the angle using this tangent relationship right there. I actually also could use sine and cosine for that if I wanted to. I always just stick with tangent and take care of it. It allows me to kind of box in how I'm attacking this. But again, I could use these relationships to also find theta once I have my r value. But in this case, finally, just to put a button on it, I would have this in polar coordinates as the square root of 29, comma 4.33. Again, when I write this as we're describing over here, in rectangular or in polar coordinates, you always write the radius value first and then the angle value. And so then it makes sense to go back the other way. You'll find that this is less ambiguous and a lot easier to go from polar back to rectangular coordinate points. But in this case right here, to convert these, I'm just going to use these two equations right here. And so again, just to make it clear, this 6 is r and the 2 pi over 3 is my theta value. So if I want to find x, all I need to do is I take r, which is 6, times the cosine of 2 pi over 3. And to find my y, I do the same thing. I'm just using my sine value. And I chose this because this is a nice known angle right here, 2 pi over 3. In this case, this becomes 6 times the cosine of 2 pi over 3 is -1/2. And the sine of 2 pi over 3 is √3 over 2. Which gives me that my x value here is -3, and my y value here would be, I get 3 √3. And again, it's really that straightforward. We don't have the ambiguity that we have when we go from rectangular to polar because we're not finding that angle and that issue in finding the angle and our inverse trig functions. But in this case right here, when I convert this polar point into rectangular, I get -3 √3.